All right, ready for a deep dive into something we experience every day but probably never really think about.
I'm intrigued. Lay it on me.
Heat.
Heat, huh? Sounds kind of basic.
It might sound that way, but we're cracking open a 7th grade science textbook to uncover the surprisingly cool stuff about heat.
Okay, you've piqued my interest. I'm ready to have my mind blown by middle school science.
Trust me, this isn't just rehashing the basics. We're talking about the stuff you never realized you didn't know about heat.
All right, count me in.
Uh-huh.
So where do we start our deep dive?
Let's start with a simple question. How do we even know something is hot or cold?
Well, our senses seem like a good place to begin. We can feel heat, right?
That's true, but our senses can be deceiving. Remember that experiment with the 3 buckets of water?
Oh, yeah, vaguely. Remind me.
Okay, so you have 3 buckets, one with ice water, one scalding hot, and one lukewarm. You stick one hand in the ice-cold water and the other in the hot.
Ouch. Yeah, I can practically feel it now.
Right. So then, after a minute, you plunge both hands into the lukewarm bucket. What happens?
Let me think. Well, the hand that was in the ice water is going to feel like it's in hot water, and the hand from the hot water will feel like it's freezing.
Exactly.
So which is it? Lukewarm water can't be both at the same time.
That's the point. It highlights that our sense of touch isn't giving us an accurate measurement, just a comparison.
Ah, so our sense of touch is relative, not absolute. Interesting.
Exactly. And that's why we can't rely on our senses alone to measure temperature. We need something more objective, more scientific.
Enter the trusty thermometer.
Right. But how do those little things actually work?
Well, most thermometers use this cool thing called thermal expansion. See, liquids like mercury expand when heated and contract when cooled.
So that little bit of mercury in the thermometer is like a tiny heat-measuring superhero, expanding and contracting to give us a reading.
You got it. The more heat it absorbs, the more it expands, pushing higher up the thermometer scale. And we've got different types of thermometers, each with its own purpose, like the clinical thermometer a doctor uses.
Speaking of which, what's the difference between a clinical thermometer and one you'd find in, say, a lab?
A clinical thermometer focuses on a narrower range of temperatures, basically just what's relevant to the human body.
Makes sense.
Lab thermometers, on the other hand, need to handle a much broader range, from super cold to super hot.
Oh, like if they're dealing with crazy chemical reactions or something.
Exactly. And speaking of temperature extremes, did you know that the original Celsius scale was actually reversed? 0 degrees was the boiling point of water, and 100 degrees was freezing.
Wait, seriously. Talk about confusing.
Thankfully, they flipped it around pretty quickly.
Good thing they did. Can you imagine the chaos? All right, so we've got a grasp on measuring heat. Now, how does it actually travel?
Great question. The textbook talks about 3 main methods: conduction, convection, and radiation. And get this.
This is the good stuff.
Each one plays a key role in how we experience heat every day. Let's start with conduction, which is simply heat transfer through direct contact.
So like when I accidentally grab a hot pan from the stove.
Exactly.
Ouch!
The heat goes directly from that pan right into your hand. Ouch, indeed.
Okay, so conduction is direct contact, like touching something hot. What about convection? That one's always been a bit harder to wrap my head around.
Convection is all about heat transfer through the movement of fluids, like water or air. Think of a pot of water on the stove.
Okay, I'm picturing it.
The water at the bottom heats up first, right?
Right, because it's closest to the burner.
And as it heats up, it becomes less dense and rises to the top.
Making room for the cooler water to sink down and get heated.
You got it. It's a continuous cycle of rising hot water and sinking cooler water, spreading the heat throughout the pot.
Like a little underwater elevator for heat. And this isn't just about boiling water, right?
Nope. Convection happens all around us. Remember those refreshing sea breezes at the beach? That's convection in action.
Oh, right, because the land heats up faster than the water.
Exactly. The warm air over the land rises, and the cooler air from the sea rushes in to take its place, creating that cool breeze.
Wow, it's like a giant convection cycle is creating our weather patterns.
Pretty cool, right? Now let's talk about the third method, radiation.
Radiation, the one that always sounded a bit mysterious. It doesn't even need anything to travel through, right?
Exactly. Think of the sun's warmth. It travels millions of miles through the vacuum of space to reach us.
So are those like tiny little rays of heat shooting at us at the speed of light?
Not exactly rays of heat, but rather electromagnetic waves. Infrared radiation, to be precise. Ever notice how a black piece of paper gets hotter in the sun than a white one?
Yeah, because dark colors absorb more heat.
Exactly. And lighter colors reflect more of it. That's radiation at work.
So that's why wearing a black t-shirt on a sunny day can feel like being in a sauna.
Precisely. And those shiny emergency blankets, they're designed to reflect your body heat back to you using the power of radiation.
It's all starting to click now. Conduction, convection, radiation. But why does any of this matter in our daily lives?
Well, think about it this way. Remember those layers of clothing we wear in the winter?
Yeah, because more layers equals more warmth. But how does that work exactly?
It's all about trapping heat. Each layer creates a pocket of air, which is a poor conductor of heat.
So we're basically creating our own personal insulation systems.
You got it. And speaking of insulation, how about those handy thermoses we use to keep our beverages hot or cold?
Thermoses are like mini miracles. How do they work so well?
It's a combination of clever design and these heat transfer principles. They have two walls with a vacuum in between. Since there's almost no air in a vacuum, conduction and convection are basically eliminated.
Ah, so it's like cutting off two escape routes for the heat. What about radiation?
They've got that covered too. The inner lining of a thermos is shiny and reflective.
To reflect the heat back to where it came from, whether it's hot coffee or a cold smoothie.
You got it. Thermoses are a testament to how understanding heat transfer can lead to some pretty cool inventions.
It's like we're wielding the power of science to control temperature. And this isn't just about personal comfort either, right? What about those hollow bricks the textbook mentioned for building design?
You're thinking of insulation on a larger scale. Those air pockets inside the bricks act as a barrier, slowing down heat transfer.
So it keeps the heat out in the summer and traps it inside during the winter.
You got it. It's a simple but effective way to make buildings more energy efficient.
So it's the same principle, whether we're talking about a little thermos or an entire building.
Exactly. Using those air pockets to control heat flow. It's pretty neat.
It really is. It shows how relevant this stuff is to our lives, even if we don't always realize it.
Absolutely. It reminds me of that saying, there's nothing new under the sun, but there's always something new to learn.
So true. We've been experiencing heat our entire lives, but this deep dive has given me a whole new appreciation for it.
Me too. It's easy to take these fundamental principles for granted, but when we stop and really think about them...
It's like seeing the world with fresh eyes.
Exactly. And that's what I love about these deep dives.
Me too. It's like we've been walking around with blinders on this whole time.
And now we can finally take them off and appreciate the science happening all around us.
Right. From a winter coat to a hot cup of coffee, it's all way more fascinating now.
And delicious. Don't forget delicious.
Yeah.
But yeah, it's incredible how something as simple as heat can open up this whole world of knowledge.
Totally. We started with something as basic as hot and cold, and now we're talking about everything from building design to thermos physics.
And remember those wacky early days of the Celsius scale? 0 degrees being the boiling point of water. Wild.
Oh man, good point. Can you imagine the confusion? Honey, bundle up. It's a balmy 100 degrees below freezing today. Yikes.
Talk about a recipe for disaster.
Glad they sorted that out. But you know, this deep dive has really hammered home the point that science isn't just some abstract thing we learn in school. It's everywhere.
It really is. It's the invisible force shaping so much of what we experience every single day.
So the next time you feel a cool breeze or warm up with a hot drink, take a second to appreciate the science at play. It's pretty amazing.
It really is. And remember, there's always more to learn.
That's right. Well, I think that about wraps up our deep dive into the incredible world of heat.
Until next time.
We hope you learned something new today and maybe even spark some of your own curiosity about the everyday wonders around us.
Stay curious, everyone.
And don't forget to subscribe for more deep dives.